Hi folks, welcome to the Key Concepts video for Chapter 8 of Math 521B, Pre-Calculus 11. In this video we're looking at systems of equations. Standard disclaimers apply, and as always you can check the video description below for a downloadable copy of the notes. So the first thing we're going to look at is verifying solutions to systems of equations. A system of equations is two or more equations in two or more variables. In this course, we're going to restrict ourselves, mercifully, to two equations in two variables. But later on, you might see more variables and correspondingly more equations. The solution to a system is the set of all ordered pairs that satisfy both equations. And you can verify those solutions just by substituting in the points, or the ordered pairs, into both equations. So here we've got a system that involves one quadratic and one line. And we're wondering if -1, -7 is a solution. So this is an x value, this is a y value. Basically we want to know, does the point -1, -7 satisfy both equations? So let me try it in the quadratic. If I put in -7 for y and -1 for x, is the equation balanced? Let's see, -1 squared is 1, -3 -5. Hey, that gives us -7. Things are balanced in the quadratic. But it's only a solution if it works for both of them. So let's check in the other one. If I put in -7 for y, is that the same as 2 times -1 minus 3? Oh, drat. That gives us -5. It doesn't work in both. So no, it's not a solution. And when you do your secondary math assessment, if this is a multiple choice question, rather than going through the process of trying to solve each of these equations or each of these systems, it's probably simpler just to check the solutions. So let's check -2, -7. Let's try it in the quadratic. So -7 will go in for y. -2 goes in for x. That'll be 4 minus 6 minus 5. Yes, this works. Let's try it in the linear. So -7 goes in for y. -2 goes in for x. Ah, that gives us -7. This also works. So since it worked in both of the functions, it is a solution. So now we can test solutions, which is probably all you need to do for a multiple choice setting. But the question that remains is, how do we find solutions in the first place? So one of the techniques is graphical solutions. We're going to graph both equations, and points of intersections are solutions. Remember when we did graphical solutions before, it was only the x value we were interested in? Well now, since it's a system of two equations, and both of them have an x and a y, we're interested in both the x and the y coordinate. So we'll solve this system by graphing. I'm going to graph y equals 3x minus 1. That's a line with a y-intercept of -1 and a slope of 3, up 3 over 1, up 3, and so on. Yep. Okay. There we go. Now I'm going to graph the parabola. And since I'm going to need to know a bunch of points, I will probably use a table of values to do this. But it's important to know what to sort of base my table of values around. What's the most important sort of x and y values, or specifically x values. So I would think about the axis of symmetry, or the x-coordinate of the vertex, is -b over 2a. So that would be -2 over 2 times 1. -1. I'm going to make that kind of my middle x value, or somewhere around the middle, and then work around there. And if I don't find intersections, I'll just put more into my table. Okay. Now I'm going to substitute those values into this. So -3 squared is 9, plus 2 times -3 is -6, minus 3, that's 0. And we can go through the rest of these. I'm just going to write them in. You can check the substitution pretty easily. So just plugging that into the equation and finding some points. So point -3, 0, -2, -3, -1, -4. Ooh, look at that. Intersection. Pretty exciting. Okay, and this point, and then 2, 5. I've got my points. I'll draw my parabola as smoothly as I can. And you can see right away, the points of intersection are at -1, -4, and 2, 5. Now we should check that those actually are the solutions. And I'm just going to check one of them. You could go through and check the other. So I'll check -1, -4. It has to work in both of the original equations. So if I put it in the linear one, the y value is -4. And I'm wondering, is that equal to 3 times -1 minus 1? Sure is. Let me check it in the parabola. -4 goes in for y. -1 goes in for x. Okay, 1 minus 2 minus 3 is -4. Yes, indeed, it works. So this is a solution. And if we did the same process for 2, 5, we'd find that it's a solution as well. Let's check out another one. Here we've got 2 parabolas. And sometimes a good place to start is simply by making a rough sketch. So this one here, it opens down. It has a vertex at 2, 1. So it kind of looks like this, just very roughly. This one over here, well, it really means y equals x minus 0 squared plus 2. So it's got a vertex at 0, 2, and it opens up. Again, very rough sketches here. But when are those functions ever going to meet? Never. So no points of intersection. Therefore, no solutions. No point of intersection means no solution. There's no ordered pairs, or there are no ordered pairs, that are going to make this true. Okay, so that's great if you have a nice graph to work from, or you can generate it easily. But sometimes that's difficult. So we want to have an algebraic approach as well. And we'll do this in 2 parts. If you're lucky enough to have them both in y equals form, you're going to equate the functions. And that's really a substitution approach. It means that wherever you saw y in one of them, you can replace it with whatever y is equal to in the other one. We solve and find the x values of intersection. And then lastly, we have to go ahead and find the corresponding y values. So we find the x values of intersection, then find the y's. So let's suppose we had the same equation that we had in example 2a, and we want to solve it algebraically. Y equals 3x minus 1, and in the other one it says y equals x squared plus 2x minus 3. Well, since y equals x squared plus 2x minus 3 in both of them, I can substitute it in for this y, or basically equate the functions. So I'll get x squared plus 2x minus 3 equals 3x minus 1. I'm replacing this y with x squared plus 2x minus 3. From there, we can solve. This is going to be a quadratic. Hopefully it'll give us the same answers that we got before. So I'm subtracting 3x from both sides. That gives me negative x. And then I'm going to have minus 2. That can be solved by factoring, or, and it would take longer, by the quadratic formula. So I get either x minus 2 equals 0, which means x equals 2, or x plus 1 equals 0, which means x equals negative 1. The solutions, therefore, have x values of negative 1 and 2. But the question is, what are the y values? And the most common mistake that people will do is they'll call that 2, negative 1 a point. It's not a point. They're both x values, and they correspond each to a point. To find the y value, I just need to sub -1, in this case, back into one of these functions. And you might as well do it in the easiest one to work with, the linear one. So this will be 3 times -1 minus 1. Oh, that gives me a y-coordinate of -4. Now for my other point, I've got a 2. So I'll sub that into either one of the functions. If you used it in the quadratic, it would work out to be the same thing. It would give you 5. There are our solutions, the ordered pairs that satisfy both equations. If we tried to do the other one, the one that had no solution algebraically, we do want to know what no solution looks like when we do it without a graph. So same idea here. I'm going to take this x squared plus 2, and I'm going to substitute it in for y over here. So x squared plus 2 negative x minus 2 all squared plus 1. I might do a little thought off to the side and say, oh, geez, x minus 2 all squared. Well, that's x minus 2 times x minus 2. Or x squared minus 2x minus 2x. So that's minus 4x plus 4. I'm just foiling that out. Don't make the classic mistake of calling that x squared minus 4. That's bad. So minus, I got x squared minus 4x plus 4 when I expanded that binomial. And the whole thing is being negativified, so I still need it in brackets. Okay, and we're just working our way through here. So this is positive 4x minus 4 plus 1. Keep going. Positive 4x minus 3. I know it's a quadratic, so I need to make one side 0. I'll add x squared to both sides. I'll subtract 4x, and I'll add 3. And now I need to solve this. Now, I might try and solve it by factoring. I try for a few seconds. I can't figure out how to factor it. So I go to the quadratic formula. And it's negative b plus or minus the square root of b squared minus 4ac all over 2a, all over 2a. Okay. And substitute in some numbers. Negative negative 4, that's 4, plus negative 4 squared minus 4 times a times c all over 2a, so 2 times 2. Okay, this is 16 minus 40 all over 4, or plus or minus the square root of negative 24 over 4. Right here, we'd say, oh dear, you can't take the square root of negative 24. This is an illegal operation. No solution. Okay, there are no points of intersection. So it will show up in your algebraic approach just like it will for your graphical approach. It'll show up looking like the square root of a negative. Or if you preferred, you could have used the discriminant to find this. In C, we'll take a look at one last situation. So I'll do the same thing. I'm going to substitute this for y in that equation. X squared minus 4x plus 9 equals 9 minus x squared. Let's move those x squareds over. So I'll have 2x squared minus 4x. Okay, so that came from adding x squared to both sides. And I'll subtract 9 from both sides. And often people get confused here because they're expecting to see a trinomial. But it's okay. If we don't see a trinomial, we can still factor. We've got a common factor, and we should always be looking for a common factor first. That's going to give us solutions of 2x equals 0, which means x is 0, or x minus 2 equals 0, meaning x equals 2. So again, the points that are the solutions have x values of either 0 or 2. Put it in whichever form you like, whichever one of those two initial equations. I think the first one looks easier. So 9 minus 0 squared, that's the 0.09. 9 minus 2 squared, that's 5. And you could go and check those. So here are our solutions. When relations are not in y equals form, things get marginally more involved, but they're really not a whole lot more difficult. We're going to use the same approach of substitution. There are two ways that you can get to that approach. You can either put your equations in y equals form and do exactly what we did before, but it might get messy. You might end up with fractions or something. The other approach would be just to isolate one variable in one equation and substitute it into the other, just like you did last year with your substitution approach. So if I have this equation here, this system of equations rather, right here, y equals 2x squared plus 3x minus 2 is my first, and 2x minus y plus 4 equals 0 is my second. I do have something solved for one variable. I know that y equals this, which means I should be able to sub it in for y in the other equation. And that's what we'll do. Okay? Or you can solve them each for y and equate them, but just make sure you don't botch your signs. This is going to be pretty straightforward, though. We just sub it in for y. So we get 2x minus 2x squared plus 3x minus 2 plus 4 equals 0. I'm using this equation, and I'm just substituting y with 2x squared plus 3x minus 2. From here, we'll get rid of the brackets. It's a quadratic, so I'll put it in a nice order. I don't really like having a negative leading coefficient, so I'd be inclined to divide both sides by -1, or you might think of it as multiplying both sides by -1. Either way, same effect. Or you might just think of it as switching all the signs. As long as you do it to both sides, everything stays balanced. From here, we could use the quadratic formula, or we could factor. And since this does factor, I'll factor it. Okay, I'm going to need x plus 2 here and minus 3 here, meaning that we have solutions of 2x minus 3 equals 0, or 2x equals 3, or x equals 3 over 2. We'll have x plus 2 equals 0 here, or x equals -2. Those are our x values for our intersections. So let's write them down. The solutions are going to happen at 3 over 2 for x, or -2, or rather, and -2. Now we just have to find the y values. You can put it in any form of the equation. You might want to put it in the linear one since there's no squaring. I'm going to put it in the quadratic just because it's already in y equals form. And yes, it'll be a tiny bit messy dealing with fractions, but not too bad. So I'll have 2 times 3 over 2 squared plus 3 times 3 over 2 minus 2. Or 2 times 9 over 4 plus 9 over 2 minus 2. That's 9 over 2 plus 9 over 2 minus 2. 18 over 2 is 9 minus 2. There we go. The y coordinate is 7. Okay, we can run it through. You could do it in your calculator if you wanted to. Similarly, if I put in -2 into that quadratic, or if I put it into the linear one, I'll get some y value. It's 3 times -2. So this will be 2 times 4 minus 6 minus 2, or 8 minus 6 minus 2. That gives us 0. Those should be the points of intersection. And we could verify them both by substituting in, or since I've got the computer here, maybe I'll get it to graph them. There's the parabola. Here comes the line. Now, I'm not quite sure what's happening, so I'll zoom in a little bit. When we do that, we can see that the intersections really are at -2, 0 and at 1.5, 7. Let's do one last one, a word problem. The main thing when we're dealing with word problems is that we need to define our variables so that when we're done, we'll know what they mean. So we have two numbers that have a sum of 13. The first number plus the square of the second number is 25. We want to find these numbers analytically. So we want to have a method. So let's define our variables. Let a equal the first number. And b could be the second number. Now let's try and make some equations. Two numbers have a sum of 13. Okay, so a plus b equals 13. The first number plus the square of the second number. First number plus the square of the second number is, that means equals, 25. So here we have a system of equations, and one of them is not linear. The way that we deal with this is isolate one letter in one of the equations. And there is an alternate technique. You could use elimination, but I think substitution is really the best way to go because it's going to work well in all cases and never be particularly cumbersome. So let's say I wanted to isolate a in this first equation. I'd have a equals 13 minus b. Now I can substitute 13 minus b in for a in the other equation. That's the whole substitution approach. So that gives me 13 minus b plus b squared equals 25. Let me write that in a better order. That'll be b squared minus b. And I'm going to need to make one side 0 because it's a quadratic. Lots of quadratics in this course. So now I can factor it. It's b minus 4, b plus 3. Okay, which gives us b minus 4 is 0, or b equals 4, or b plus 3 equals 0, which would mean b is negative 3. So the points are, if we think of them as points, the second number is either positive 4 or negative 3. If the second number is 4, we could use any one of these three equations to check it and find the first. But I think this is the easiest one. A equals 13 minus b. So 13 minus 4, the first number would be 9. If the second number is negative 3, well, a is 13 minus b, so 13 minus negative 3. The first number must be 16. Now, does this work? In both cases, these numbers add to 13, so they satisfy the first equation. The first number plus the square of the second, so 9 plus 4 squared, is that 25? Yes, it is. Let's check the other one. 16 plus negative 3 squared, is that 25? Yes, it is. So there are two possibilities here in terms of pairs. The numbers are 9 and 4, and 9 would have to be that first number, or 16 and negative 3. And of course, you might have different types of word problems that come up with systems of equations, but this whole idea of making sure you define what it is you've found, that's going to help you out in interpreting your answer. I hope that you found this helpful, and I'll see you for the next one. Take care.